Alright, 3.8 derivatives of inverse trig functions. I'm going to start with doing it the long way. You wouldn't have to do this every time, just kind of proving where it comes from the formula. If we have y equals inverse sine of x, we could find the sine of each side. So I'd have sine of y equals the sine of the inverse sine of x is x. And we're looking for the derivative, so we're going to go d dx of each side, derivative. We're looking for dy dx. So the derivative of sine y is cosine y into y dx, or I'm going to do y prime equals the derivative of x is just 1. So then y prime equals 1 over cosine y. So the derivative of inverse sine of x is 1 over cosine y. Not ideal because we're looking for it in terms of x, and that's in terms of y. So we go back to a Pythagorean identity. If I know the sine squared of something plus the cosine squared of something, we know that's always equal to 1. And if I wanted to solve for cosine here, cosine y would be square root of 1 minus sine squared y. It's plus or minus, but cosine is positive because it's between negative pi over 2 and pi over 2. Okay, so that's what cosine y is, so we could substitute that. And we know sine y is x. Okay, that's how they're related. Sine y is equal to x. So y prime is equal to 1 over square root of 1 minus x squared. So this is the derivative of inverse sine x. Now, generally speaking, the derivative of inverse sine of u up camera. There we go. The derivative of inverse sine of u is equal to 1 over square root of 1 minus u squared, and then times the derivative of u, so times du dx. So that's the general formula for the derivative of inverse sine. So an example, if I wanted to find we'll just do x squared. So if y equals inverse sine of x squared, and the derivative would be 1 over the square root of 1 minus, our u is x squared, so it'd be x squared squared, so x to the 4th, times the derivative of u, which is 2x. So you can move that to the top, and we have our answer. You could do the same thing for like if we wanted to do inverse tangent x, you end up doing another Pythagorean identity, so tangent of each side. This is doing it the long way, kind of the proof. So tangent of y equals x. And now we could find the derivative, secant squared y times y prime equals 1. 1 divided by secant squared y. And we know that 1 plus tangent squared y is equal to secant squared y. So we could replace that with 1 over 1 plus tangent squared y. And we know that tangent y is x, so y prime would be 1 over 1 plus x squared. So this is the derivative of inverse tangent x, 1 over 1 plus x squared. The general form would be the derivative of inverse tangent u is equal to 1 over 1 plus u squared, and then times du dx. And then these are all found on Carl. So we've got inverse sine right here. We've got inverse tangent, and we've got inverse secant. those are just 3 of them, but in the book there's identities that relate inverse sine and inverse cosine. Let's see if I can find it here. Okay, so the inverse cosine is equal to pi over 2 minus inverse sine, and then cotangent and cosecant. That's how they're related. So what we can do is, if we wanted to find, as an example, the derivative of inverse cosine of, we'll just say 3x, we could rewrite that as pi over 2 minus the inverse sine of 3x. And then when we do the derivative of pi over 2 just disappears, it's 0. So basically, if you just want to remember, if we're finding the derivative of inverse cosine of something, it's the same as the derivative of negative inverse sine of that. So just find the derivative of inverse sine of 3x and make it negative. So derivative of inverse sine of 3x is 1 over square root of 1 minus u squared times 3, and then we would just make it negative. So y prime would be negative 3 over square root of 1 minus 9x squared. So that would be your derivative. And then the same is true for inverse cotangent and inverse cosecant based on those identities. Sorry, did you see it? There we go. Okay, I want to do one more example for sure. See if I can do anything else. No, I'll just make one up here. Okay, so we're dealing with inverses, and all functions have inverses, but not all inverses are functions. So you can always find an inverse, but the inverse is not always going to be a function. And that's whether it's 1-to-1. If it's a 1-to-1 function, that means it passes the horizontal line test. This is 1-to-1 because you cannot draw a horizontal line anywhere and hit it in more than one spot. So this is 1-to-1, therefore its inverse is a function because it's 1-to-1. And this is not 1-to-1, but it does have an inverse. Remember, the inverses are always symmetrical with y equals x. So if I was going to draw my y equals x, the inverse of this, oh boy, let's see, look like that. There's my inverse. Notice they're symmetrical across the line y equals x. It's not 1-to-1, therefore its inverse is not a function. So the original fails the horizontal line test, hits it in more than one spot, and because of that, its inverse is not a function. You can see the green inverse is not a function because it fails the vertical line test. Alright, so that's just kind of some background information about inverses. If I know that, let's say f of 1 equals 4 and f prime of 1 equals, we'll say 2/5. Okay, what is f inverse of 4? Well, if this was our function, and I was going to just plot what we know that's the line y equals x. F of 1 equals 4, so if I go over 1, up 4, it exists right here. That's f of x, and then f1 comma 4 exists on f of x. Well, what point on the inverse has to exist? Well, if it's symmetrical to y equals x, it's reflected across it. So 1, 2, 3, 4, up 1, 4 comma 1. If this is f of x, this would be f inverse of x. 4 comma 1 has to exist on the inverse because the domain and the range switch. So 1 comma 4, then 4 comma 1 exists on the inverse. Okay. We know that the derivative of the original at 1 is 2/5, so up 2 over 5, so we'll say it's kind of like this. That's our derivative at 1 comma 4. Well, if it's going to be symmetrical with the line y equals x, then the derivative at the inverse of the corresponding point, so f inverse prime of 4, so the derivative at the f inverse of 4 has to be well, it looks like that. So if it's symmetrical with y equals x, but it's not perpendicular to it, it's the reciprocal of it. So you just find the reciprocal of our original function, and it'll be the derivative at the corresponding inverse point. Okay, so if that's 2/5, then this would be 5/2. And they have that, I'd say half the time, maybe a third of the time, there'll be a question on the AP exam about that. They'll just give you the function, like 1 point, give you the derivative at that point, and then they'll say, what's the derivative at the f inverse of 4, and you just know that it's the reciprocal.